Okay. Hello everyone and welcome back. As usual, we have a few minutes before class, so you can ask me any questions if you like. And while I wait for that, let me ask you, or not ask you some questions, but let me tell you sort of a story that's happened to me a few times, once while teaching this course and once while teaching the fourth year algorithms course. And the story has to do with gambling, and it's not an uncommon one. So I had a student come to me with a claim that they had a perfect system for gambling, so for beating the system. And it almost didn't matter what the game was, as long as it was a game that you could bet on with different values of bets. So you could think of it as, you're betting on the outcomes of coin tosses. There's a casino who tosses the coin, and you are the player in the casino, and at each time you can bet any number of dollars that you want on whether the coin is going to come up heads. So if the coin comes up heads, you get your bet plus your bet back, so twice as much. And if it comes up tails, well, you lose your bet. And so the strategy that this student had, which many people fall for this, is well, there's a way to beat this game, which is my first bet is $1, and then the casino tosses the coin, and if I win $1, so I win my original $1 back plus another $1, so I'm ahead by $1, and I walk away at that point. Okay, and if I lose, then I'll play again, but this time I'll bet $2. So I've lost $1 already, but if I win on that second round, I will win $2, which means that I win back my original $1 plus the one that I lost in the previous round. So I'm ahead $1, and I'll leave at that point. So I leave ahead. And if I lose those first two rounds, well, next time I'll bet $4. And you can add that up and realize, okay, if I win then on the third round, I'll still be ahead by exactly $1. And so the strategy in general is, if you win, leave, and if you lose, just double your bet from the previous time. And indeed, by the time you leave, you will leave with $1 more than you started with. So this seems great. It seems too good to be true. Say hi to my new cat, one of my new cats. So during today's lesson, I want you to remember that strategy and think about what's wrong with it. So we'll discuss something that's relevant to that strategy today, and then you think about what's wrong with that. Why doesn't this strategy work? Okay, so today we're going to talk about what are called indicator random variables. It's a big fancy name for actually something that's extremely simple. An indicator random variable is just a random variable that only takes on two values. It could be 0 or it could be 1, so two specific values. So call it an indicator random variable, presumably because one indicates some event that we're interested in, and 0 indicates the non-occurrence of the event that we're interested in. And here's a fun fact about indicator random variables that's trivial. If you have an indicator random variable b, then the expected value of b, well, remember there's two ways to get the expected value. We can either sum over all the possible values of B, or we can sum over all the elements of S. For indicator random variables, it makes a lot of sense to only sum over the two possible values of B because there's only two of them. So we do that here, and the expected value is 0 times the probability that B equals 0, plus 1 times the probability that B equals 1, but that really simplifies, right? That's just the probability that B equals 1. So super useful fact about indicator random variables is their expected value is really easy to compute. You just need to compute the probability that B equals 1. Okay. All right. So let's look at first a really easy example. We'll take a random bit string, so B1 through Bn, and what does that mean? That means that B1 through Bn is a vector of length n whose elements are either 0 or 1, so that's the set of possible outcomes, that's the sample space, and random here is supposed to mean uniformly random, so the probability of getting any particular bit string is just 1 over the size of that set, and we've seen many times that the number of bit strings of length n is 2 to the n, so each one has probability 1 over 2 to the n of occurring. Okay, and let's define a random variable, which x, which you get by just counting how many ones are in your bit string. Okay, so I have a bit string consisting of n bits, a random one. X is just the number of ones in this bit string. Okay, so formally, this would be x is a function from B1 to Bn onto real numbers. So x of B1 to Bn is just you sum up all the bits, but the zeros don't count, so really you're just counting the number of ones. So first of all, we think about this for a second. We want to know the expected value of x, so the expected number of ones in a random bit string of length n. Well, intuitively the answer should be n over 2, right? So each bit is a 1 with probability a half, and there's n of them, so we expect that n over 2 of them will be ones. But if we try and apply the definition of expected value, well, we have these two definitions. One, you can sum over all the possible, you can sum over the elements in S, or you can sum over the possible values of x. Well, the number of elements in S is 2 to the n, so that would be a really complicated sum if we tried to sum over all the possible outcomes. On the other hand, the number of different values that x can take on is only n plus 1. Right? We can have 0 ones, we can have 1 1, we can have 2 ones, we can have 3 ones, all the way up to n ones. So there's n plus 1 possible values. So it seems like the way to tackle this is to sum over those things. So we sum from k going from 0 to n. The value of this thing, so k times the probability that x equals k. So what's this probability that x equals k? Well, for that, we have to count the number of bit strings of length n that have exactly k ones. That's something we've done before. It's n choose k. And then we have to divide that by the total number of bit strings. So that's what this sum comes out to. And then there's a giant leap where we say, okay, that equals n over 2. And that's not at all obvious. So even this thing that should be a trivial exercise, just by applying a definition of expected value, it's not obvious that this is, I mean, everything is correct up to here, but how does this turn into n over 2? I mean, if you're good with these things, then you can figure this out, but there should be a better way to do this. And there is, and it's using indicator random variables along with linearity of expectation. So one thing you can notice is that for any I, so pick any bit here, bit I, the probability that bit I is equal to 1 is equal to the number of bit strings in which there's a 1 at position I divided by the total number of bit strings. So if I fix position I to be 1, then there's 2 to the n minus 1 ways of choosing all the other bits, so all the bits except for bi. And then the total number of bit strings is 2 to the n, so that's a half. So the probability that a particular bit I is equal to 1 is just a half. Okay. So define a random variable xi, which, well, I mean, it's 1 if bi is equal to 1, and 0 if bi is equal to 0. So xi is just bi, the value of the ith bit. And now notice that x, the sum of these things, well, it's just the sum I equals 1 to n of xi. And therefore, the expected value of x is equal to the expected value of that sum. And we saw linearity of expectation says that the expected value of a sum is the sum of the expected values. So what does that look like? That just says that this expected value of this complicated sum is just the sum of these expected values. So now to continue, we need to know the expected value of xi. But what's xi? Xi is an indicator random variable. It only takes on the values 1 or 0. And the probability that it's equal to 1 is 1/2. So by this, the expected value of xi is equal to 1/2. So it doesn't depend on I. This is a sum with n terms. Each term is 1/2. So this is n over 2. So indeed, the expected number of ones in a random bit string of length n is n over 2. You get that very easily using indicator random variables, and not so easily if you just use the definition of expected value. So even for something as simple as that, these indicator random variables make life much, much easier. Okay. All right. So let's look at another example. So we will again stick with this random bit string, and here's a definition. We say that bi if bi is equal to bi plus 1 is equal to bi plus 2 is equal to, and so on, bi plus k minus 1, then we say that I starts a run of length k. Okay, so what does that look like? Right, we have this bit string. Suddenly we get to bi, and from bi up to bi and the next k minus 1 bits are all the same. Okay. So total of k bits here, and then whatever else happens. Okay. So if that happens, then we say bi starts a run of length k. And it doesn't tell us anything about exactly the next bit after this. Could be a 0 or it could be a 1. So it might be a 0, it might be a 1. So anything goes before that, anything goes after that, but these bits are all equal. And they could all be equal to 0, or they could all be equal to 1. So again, k bits. All right. So you might think that in a random bit string, you're not going to find runs of length k for very big values of k, right? I mean, that's the same thing as saying a run of length k means that I tossed a coin from this point on, I tossed a coin k times, and it came up, let's say in this case, tails every time, or in this case it came up heads every time. And I don't think that in a random sequence of coin tosses you're going to see a whole bunch of tails in a row or a whole bunch of heads in a row. Or maybe you will. So let's look at question. What is the expected number of runs of length k in this random bit string? All right, so how are we going to figure that out? Well, you can guess we're going to use indicator random variables. And we'll do that by saying for each I in runs can start at position 1, so runs of length k, and they can go all the way up to position, this would be n minus k plus 1. Define xi is equal to 1 or 0, and it's 1 if this thing starts a run. So that means bi equals bi plus 1 equals, and so on, equals bi plus k minus 1, and 0 otherwise. And it's not hard to convince yourself that, well, the expected value of xi, which is equal to the probability that xi equals 1, is going to be equal to what exactly? We need to know how many bit strings there are that have a run of length k at exactly these positions. Well, that means these positions are either all 0, so the number of such bit strings is 2 to the n minus k, so we fixed k of the bits equal to 0, and then the rest can be, the other n minus k bits can be whatever they want, or the bits are all equal to 1, and the rest can be whatever they want. So that's another 2 to the n minus k. So this probability is 2 times 2 to the n minus k divided by the total number of bit strings is 2 to the n. So this is 1 over 2 to the k minus 1. Yeah. So that's the expected value of xi, and therefore the expected number of runs of length k is just the sum over all those i's. Sum I equals, we start at 1, we go up to n minus k plus 1 xi. We want the expected value of that thing. Always, when we have an expected value of a sum, we nearly always want to take the sum of the expected values. I mean, that's sort of the whole reason for indicator random variables. We've already computed the expected value of xi. It's just the 1 over 2 to the k minus 1. The number of terms here is just n minus k plus 1, and they're all the same. And so that's the answer. Okay. So think about this for a second. And let's take, for example, n to be, oh, I don't know, 1024. And why 1024? Because that's 2 to the 10. So let's look at an example. Take n is equal to 2 to the 10, and let's take k is equal to 10. Plug that into this formula here. We get n is 1024 minus k is 10, so minus 10 plus 1 over 2 to the k minus 1 is 2 to the 9, which is 512. So this is 1015 over 512. So that is, you know, just a little bit less than 2. 1024 over 512 would be 2. This is just a little bit less than 2. So what does that mean? Well, that means that if we toss a coin 1024 times, then we will expect that there's 2 places in that sequence of coin tosses, or that sequence of zeros and ones, where we will see the next, this location I, and the next 9 locations, so 10 locations in a row, where those coin tosses all came up the same. Or in the bit string formulation, where we have 10 bits in a row that are all the same. And we expect to find that twice, actually, in that the 2 such locations in this bit string. Okay. So think now, go back to your gambler who's doing this. So now think about this gambling thing that I mentioned if you were here in the first 5 minutes, and think about what that means for this gambler if he is going to try and use this, his strategy for a long time to make a lot of money. Why is expected value xi equals 1, 2 times 2 to the, okay, so the probability that xi equals 1, for that we need to count the number of bit strings where xi equals 1. So those bit strings where xi equals 1, they look like this. We have position I and k zeros in a row, or we have position I and k ones in a row. So the number of bit strings that look like this, well, they can have anything here and anything here, and the number of bits here and here is n minus k. These bits can have any values, so there's 2 to the n minus k of bit strings that have a run starting at position I, and it's a run of zeros. Okay. Similarly, there's 2 to the n minus k bit strings that have a run starting at position I, and it's a run of ones. So that's another 2 to the n minus k. So that counts the number of bit strings that have a run of length k starting at position I as this plus this. So 2 times 2 to the n minus k. And to turn that into a probability, we have to divide by the total number of possible bit strings, which is just 2 to the n. Yeah. So the observation is that gambler's strategy can only work if the gambler is always carrying around an infinite amount of money to handle long losing streaks. And it doesn't have to be you don't even have to play this thing that long, right? So remember, the gambler's strategy only wins him $1 each time he walks away. So if he wants to make a significant amount of money, he's going to have to use that strategy a lot of times. And this thing just says, well, if he uses it enough times, and in fact, it's not even 1,000 times, because this is the whole sequence of plays, and each time he uses it, it takes a few plays. But even if he plays 1,000 games, then somewhere along the way, he's likely to run into a losing streak of 10 in a row. And that means that last bet that he has to make has to be 2 to the power $10, or $1,024. And so if he's not carrying that much money, he can't continue his strategy, and he loses. And he doesn't just lose a bit; he loses big. Actually, he loses $1,023 at that point. Okay, good. So there's an example of this. And let's go back and view something we've seen already from this lens of expected values. And the thing that we saw already was this birthday paradox that said, if you put, if you put 23 people in a room, then the probability that 2 of them have the same birthday is actually a little bit bigger than a half, even though there are 365 possible birthdays. So, so the setup was, you have n people, and you have d days in a year. And so the set S was label the days of the year 1, 2, 3, 4, 5 up to D, and take an n vector of that, right? This is, first element is person 1's birthday, the next element is person 2's birthday, the next element is person 3's birthday. And this was supposed to be we were assuming things were uniform, so and we were asking what's the probability that there's at least 2 people with the same birthday, and we saw that the better way to tackle that was with the complement rule, looking at what's the probability that everybody has a different birthday, which wasn't very high once n gets around the square root of d. But here's another way to think about this that also explains why, that gives some more intuition. Let's look at let x equal the number of pairs of people that have the same birthday. Okay. And of course, I want to know the expected value of x, otherwise we wouldn't be talking about this in this lecture. And I want to use indicator random variables. So you just say for each I, j in 1 to n, with I not equal to j, say, let xij equal 1 or 0, and it's 1 if person I and person j have the same birthday, and 0 otherwise. So if I want to know the number of pairs of people that have the same birthday, well, that's just, let me just count over all the pairs of people, and we'll count a 1 if those 2 people have the same birthday, and a 0 if they don't. In the end, that gives me the number of pairs that have the same birthday. And another way to write that a little more carefully is this just means that x is equal to the sum. I take I running from 1 up to n minus 1, and I take j running from I plus 1 up to n of xij, and therefore the expected value of x is the expected value of that sum. We use linearity of expectation to take the expected value inside, sum still running over the same variables. So we need to know the expected value of xij. Well, xij just depends on person I and person j. So, it's like you have 2 people. What's the probability that they have the same birthday? Each of them has a birthday which is any of the uniformly one of the D days of the year. So you can think of it as person I picks his birthday. What's now the probability that person j picks the same birthday as person I? It's 1 over d. If you want to do it more formally with the whole sample space, you do something like we did with random bit strings. You count the number of outcomes where I and j have the same birthday and the number of outcomes divided by the total number of outcomes. But you'll get the same answer. It's 1 over the number of days in the year, 1 over d. So the expected value of xij is 1 over d. So we have this double sum with 1 over d. And how many terms are in this sum? Well, this is just summing over all the distinct values of I and j. So it's just the number of, and I and j are ranging from 1 to n, so it's the number of 2-element subsets of 1 to n. It's n choose 2. And so that's the expected number of pairs of people who have the same birthday. And n choose 2, remember, is n times n minus 1 over 2. So that thing is n times n minus 1 over 2d. And that's why you don't need that many people. Here we have a n squared, right? So this is n squared minus n over 2d. So it's roughly when n squared becomes bigger than 2d, so that happens around the square root of 2d, you get that the expected number of pairs of people with the same birthday is bigger than 1. And that, for d equals 365, that happens with n equals 23. You start to expect to actually see at least one, you see a pair of people that have the same birthday. Why aren't we multiplying by 2 to the n minus k times 2 to the n minus k? Okay, so that's a step back to the counting that's now gone. Why are we not multiplying? Because we're estimating the size of a set, which is the number of bit strings that have a run of length k starting at position I. And we're using the sum rule, because that set can be split up into 2 sets. One of them are runs that start at position I, and it's a run of zeros, so it has all zeros from positions I to I plus k minus 1. The other set are the set of runs that start at position I and consist of all ones. Okay. Those are 2 disjoint sets, and the union of them is the set of all bit strings that have a run of length k starting at position I. Okay. So by the sum rule, the size of the set of the first set, the one we're trying to count, is just the sum of those 2 sizes. Okay. Yeah, and just here, a numerical example, if I do 23 choose 2 divided by 365, you get something like 0.691 Okay. So you get that the expected number of pairs that have the same birthday is, it's still less than 1, but it's not that much less than 1. Okay? And since the actual number of pairs is either 0 or bigger than 0, this kind of almost means that there must be a good chance of them being at least 1. It's not quite, there's a little bit more you have to do to really make that rigorous, but already, like, the expected number of pairs is not a small number now. It's not close to 0. It's actually getting closer to 1. Okay. All right, so lots of nice sort of problems and applications there. Let's do something really computer sciencey. So I think we can remember what an indicator random variable is. Now, it's not a complicated definition. It's a variable that takes on the values 0 or 1. So here's an algorithm that you may have seen before. It's called insertion sort. Takes an array A of length n, and just so we know what we're talking about, A is indexed starting at 0 and going up to position n minus 1. So it does the following. For I equals 1 to n minus 1, j is equal to I, while j is bigger than or equal to 1, and a at j minus 1 is bigger than a at j, swap. Okay. So this is the insertion sort algorithm. Suppose that this was my array A. So it tries to grow a sorted array, or turn A into a sorted array, starting at the beginning. So remember, these are the indices of my array, 0 through n minus 1. So it starts with 1 here because this subarray, consisting of only one element, is sorted. So one element by itself is always sorted. The problems only come when you get 2 or more elements. So it looks at this thing. So starts at I equals 1. Here's I. Sets j equal to I. So now j is looking at this thing. And as long as j is bigger than or equal to 1, and the value at position j minus 1 is bigger than the value at position j, it swaps these two things. So in this case, it's going to swap 5 and 2. It decrements j, and then the while loop is over because j is not bigger than or equal to 1 anymore. And so in the next iteration, it starts with 6, sets j equal to 6, compares what's at position j and what's at position j minus 1. If they're in the wrong order, it swaps them. If they're in the right order, it stops. And in this case, it stops because in this case, a at j minus 1 is smaller than a at j. 5 is smaller than 6. So the while loop ends immediately. And then it moves to here. And now again, it stops immediately because 7 is already bigger than 6. Moves to here. And again, stops immediately because 8 is bigger than 7. And then maybe there was one more element. So let's put in 4 here. It moves to this. And now it compares. 4 and 8. 4 is smaller than 8, so it swaps them. Now it compares 4 and 7. 4 is smaller than 7, so it swaps them. Now it compares 4 and 6. 4 is smaller than 6, so it swaps them. Now it compares 4 and 5. 4 is smaller than 5, so it swaps them. And now it compares 4 and 2. 4 is bigger than 2, so it stops. Okay. So it's called insertion sort because you can always think of it as it has a sorted prefix, an already sorted prefix, and then there's a new element that it inserts into the correct location in that prefix. All right. So one thing you might notice is the running time of this thing is kind of variable, right? We have a for loop that executes exactly n minus 1 times, but inside there we have a while loop, and how many times that executes kind of depends on what's in the array. Like we saw in this example, there were a whole bunch of times that the while loop didn't really execute at all. I mean, the body never executed even once. And there were other times, for instance, when we put in for, where it executed a lot. So we'd like to know, well, what's the running time of this thing? And really the only real sort of variable here is, you know, how many times did these two things execute? This is the part that we don't really understand. That depends on what the contents of A are. For example, if A is already sorted, then these things never execute. If A is already in sorted order, all that happens is you scan the array, and each time you realize that the next element is already bigger than everything you've seen. So this never happens. On the other hand, if the array is in reverse sorted order, well, then you can maybe figure out that actually the number of times this happens ends up being n choose 2. And one way to see that is to realize that every pair of elements, if the array is in reverse sorted order, every pair of elements is in the wrong order. Right? So the bigger one, for every pair, the bigger one is appearing before the smaller one. And the only way in which this thing changes the order between a pair of elements is to swap that pair. Right? Those swaps only affect the order between two elements. So if two elements are in the wrong order, then at some point insertion sort has to swap them. All right, and so, you know, the question is, if, so how does it do on average? Let's say if A is a random permutation, then what is expected number of times this thing here, star, executes? Okay. Let's call this x. The number of times these two lines execute, let's call that x. So complicated looking thing, and in fact x here really is the running time of this. I mean, x plus n is the running time of this algorithm, so we'd like to know that. Well, here's how you can do that. And I've said it already, right? So for each x and y, where 1 is less than or equal to x, is less than y, is less than or equal to n, define, I'm going to use I for indicator, ixy is equal to 1 if y appears before x in the input array. 1 and 0 otherwise. Okay. So, for example, if this were my input array, before I start moving anything around, then I would have, for instance, I 1, 2 is equal to 1 because 1 and 2 are in the wrong order. I would have I 1, 3 is equal to 0 because 1 comes before 3. Okay? And I 2, 4 is equal to 0 because 2 shows up before 4. So you get the idea. In fact, these things are called inversions, meaning that x is smaller than y, but y appears first in the array. So it's an inversion. And what we notice now is that x is going to be equal to, so we count from little x, 0 up to n minus 2. Little y counts from x plus 1 up to n minus 1 of I xy. So, right, the only, for instance, in this picture here, let's put in let's make something a bit more interesting. So in this picture here, for example, I47 is an inversion. Okay, so I47 is 1 because 7 appears before 4, and 7 is the larger of these two things. Now, when I run insertion sort, that means at some point I'm going to consider the smaller of the two. So at some point I'm going to get to this array where this is index I. And now I'm going to insert this thing into its proper location in the sorted part of the array, which means that it's going to have to pass over 7. And the only way that it will do that is by a swap with 7. Okay? So this line will execute exactly when a at j minus 1 is equal to 4, a at j minus 1 is equal to 7, and a at j is equal to 4. I don't know what j is going to be by then, it doesn't matter, but 4 and 7 will swap. And they're going to swap because this line executed. Okay? So really, that says that the number of times this executes is really just the number of inversions in the permutation, and that's what this is counting. So that means that the expected value of x is the expected value of the sum. Now that is a monster. Looks difficult, but we get to use the sum of the expected values. And IXY is a indicator random variable, so all we need to know is the probability that it's equal to 1 to know its expected value. And let's think about it for a second. So this says in a random permutation of 1 to n, I look at two integers, x and y. X is smaller than y. What's the probability that in the random permutation y appears before x? Well, intuitively, that should be the same as the probability that x appears before y. Right? Somehow, if everything is random and there's this big symmetry, y is just as likely to appear before x as x is to appear before y. So that means that we think that this should be a half. And we can actually, we can make that precise. So we think that the probability that this thing is, that y appears before x is a half. And you can make that precise using, using the bijection rule, because you can just say, take all your permutations and break it up into two sets, A and B, and set A is permutations where with x before y, and this is permutations with y before x. And if I look at one of the elements in here, I'll see a bunch of stuff, and then I'll see x, I'll see a bunch more stuff, and then I see y. Over on this side, there's a permutation that looks exactly the same except for x and y. Right over here, there's a permutation that looks exactly the same as this one, except when x shows up here, y shows up here. And then when y shows up here, x shows up here. And there's exactly one permutation on this side that matches this one. So there's a bijection from A to B. And so the bijection rule says that A and B must have the same size. And now, together, these are all the permutations. So the number of permutations of 1 through n is n factorial, and half of them are here, half of them are here. So that means the size of this one, in particular, is n factorial divided by 2. So all the permutations where y comes before x, how many are there? There's n factorial over 2. How many permutations are there in total? There's n factorial, so the probability that y shows up before x is just 1/2. N factorial over 2 divided by n factorial. Okay, so this is the double sum of 1/2. And how many terms are in this double sum? Well, this is just listing out all the pairs of indices from 0 to n. So you pick two indices, x and y, where x is smaller than y. So those are just the number of two-element subsets of 0 through n minus 1. So this is equal to n choose 2 divided by 2. Okay. So the answer is n choose 2 divided by 2, which is equal to n times n minus 1 over 4. Okay. So the point is that, right, insertion sort can be very fast. If you give it a sorted array, it's very fast. It actually runs in linear time because this never executes. If you give it a reverse sorted array, it's very slow because this executes n choose 2 times. And if you give it a random array, well, it's twice as fast as if you give it a reverse sorted array, but it's not great still, right? So it's not that the random one somehow is really close to the sorted one. No, it's about halfway between the sorted one and the very slow reverse sorted one. So still not efficient even on random inputs. Okay, but all this to illustrate that we didn't do anything particularly, there were no hard computations here, right? Nothing really complicated, no weird binomial sums or anything, and we managed to understand what's kind of it's a non-trivial algorithm. There's a lot going on here, and so we managed to get it. Okay. And one more really important example, which has tons and tons of applications, is what's called the theory of records, but I'll think of it in terms of finding the, let's say finding the maximum. So here you say max is equal to maybe minus infinity, and then for I is equal to 0 to n minus 1, if a at I is bigger than the max, then max is equal to a at I. Okay. Super simple function. This is a for loop that always executes n times. This is just a straight line of code. This if statement always executes n times. In particular, the condition is always tested n times, but sometimes this line of code doesn't execute. And sometimes it does. So the question is, the only question is, how often does this execute? And again, there's sort of an obvious case. In the worst case, the array looks like this. So it's in sorted order. And in which case, every time we look at a new element, it's bigger than the max we've seen so far. So this always executes. Okay. So one answer is it could execute n times. On the other hand, if the array is in reverse sorted order, then the first thing we look at is the maximum. And after that, everything we look at is smaller, so this line never executes again. So any array that we give you, the number of times this executes is something between 1 and n. If it's a sorted array, it's n. If it's a reverse sorted array, it's 1. So the question is, what happens in between? What if it's a random array? So let's say x equals the number of times line star executes when a is a random permutation of 1 to n. Okay? And we want to know what's the expected value of x. So while I erase this board, think about what you think the answer is. What's your guess? Okay. Um, so guesses are n minus 1 over 2, n choose 2 over 2. It can't be n choose 2 over 2 because that's much bigger than n, and it's never more than n. But, you know, guided by our last example, basically there was, in the last example, the fewest number of times it could execute was 0, no swaps, and the largest number was n choose 2, and the answer, the truth, was actually halfway in between those things. It was n choose 2 over 2. So here the things are 1 and n, so n minus 1 over 2 seems like a reasonable guess, like, you know, halfway in between the extreme values. So let's work through it and see what we get. So we'll define, so I changed the indexing here just because it's going to be a bit more convenient for calculations. This array is indexed from 1 through n, and so this loop runs, I runs from 1 to n. It'll make calculations a little bit simpler. Of course, it doesn't change anything. Xi, for each I in 1 to n, xi is equal to 1 if this line executes during the ith iteration of this loop, and it's equal to 0 otherwise. So then certainly x is equal to the sum I equals 1 to n of xi. Right? X is the number of times this line executes. Xi is the indicator variable that this line executes during the ith iteration. So the number of times is really summing these xi's. Good. And another way to think of xi, so instead of thinking about the code here, what does it tell us about the array? Well, it means that if this line executes, it's because a at I is bigger than max, and max at this point is equal to the maximum value in a1 up to ai minus 1. So a at I is bigger than that, so that means a at I is the maximum value in a1 up to ai. Right? So this happens exactly when ai is the biggest value you've seen so far. Okay. So now what's this expected value of xi? Well, intuitively, what's this a1 up to ai? It's just a bunch of distinct numbers, and it's the beginning of a random permutation over 1 through n. Okay. So it's I numbers that are all different, and somehow it's, if I keep going, what I'll eventually get is a random permutation of 1 to n. But one of those numbers is the maximum. And intuitively, if this is a random permutation, the maximum should be equally likely to be anywhere, right? The maximum should show up, you know, could show up here, 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 at position 1, at position 2, all the way up to position I. So intuitively, I think the answer, or we can intuit the answer, should be 1 over I. From these I elements, the probability that the maximum one is the last one should be the same as the probability that it's the first one, which is the same as the probability that it's the middle one. So they should all be 1 over I. So that's the intuition. And to really verify that intuition, we'll use the product rule. So how do we get a permutation where this one is larger than, is the largest of this set? So here's what you do. So I want to know let's say A is permutations of 1 to n such that AI is equal to the max of A1 up to AI. And what's the size of A? So we use the product rule, and we choose, so, you know, step 1 is choose A1 up to AI. So I want a permutation where AI is the maximum of these things. So first thing I do is I choose the values that go there. So that's going to be n choose I. Now, step 2 is put max of A1 to AI at position I. So I chose those first I values. One of them is the maximum. I'm going to stick it there in my permutation. There's only one way to do that. After I've chosen the values, there's only one of them is the max. I'm going to put it there. But there's still I minus 1 other values whose order I get to choose. They all go before this thing. So choose the order of I minus 1 others. How many ways are there to do that? Well, it's just I minus 1 factorial. And then finally, so that covers the permutation A1 up through AI. I still have n minus I other values that I can do whatever permutation I want here. Okay. And then choose permutation of the other n minus I. Okay. And so that is a procedure that will generate any permutation where AI is the max of the first I elements. And so by the product rule, the number of such permutations is going to be n choose I. We get an I minus 1 factorial. We get a n minus I factorial. And if you cancel this out carefully, you'll see that what you're left with is just 1 over I. So it's exactly what we expected. The likelihood of the ith element being the max so far is exactly 1 over I, the probability of that. And so now we're done. So the expected value of x is the expected value of the sum, which is the sum of the expected values. But now it's not so clear. This is the sum, I equals 1 to n of 1 over I. Okay. Now this you may or may not have seen before. This sum is really important. It shows up all of the time in probability and, well, all kinds of areas of mathematics. So it's so important that it has a name. It's called the nth harmonic number. And what can I tell you about the nth harmonic number? Well, let's draw a picture of what this nth harmonic number looks like. So the first term is 1 over 1. So if this was to scale, this first term here would be a square, but it's not to scale for a reason you'll see soon. The second term, when I equals 2, is 1/2. The third term, when I equals 3, is 1/3. And then the next one is 1/4 when I equals 4. And then finally, this goes all the way up to the end where we're getting, this last thing here is 1 over n. So, so here I've drawn a bunch of rectangles, and the areas of these rectangles are exactly equal to this sum, the nth harmonic number. Right? First one has area 1, second one has area 1/2, third one has area 1/3, area 1/4, and so on. So we want to get a feel for this because we think it's like n minus 1 over 2 was our intuition, although maybe that's starting to go away from us now. So let's look at a particular function. So let's look at the function y equals 1 over x. So that function is here. This is 1 over 1. So that's x is 1, y is 1. Here when x is 2, y is 1/2. So that puts that function there, and there, and there, and there. And it's a smooth function, right? This particular function is defined for all everything except for x equals 0. So in particular, it's some smooth function like this. All right. Now, I'm interested in the areas of these rectangles. And we've seen, or you have seen recently, me not recently at all, that when we have functions and areas, there's this whole calculus that deals with these things. But in particular, the area under this curve here, the red area, there's a name for that. It's the integral. And it would be the integral going from 1 to n of 1 over x. That's with respect to x. So that's the red area, is this integral. And this red area contains 1/2 plus 1/3 plus 1/4. It contains all the rectangles except for this one here. So that means that h of n is less than or equal to, you take the red area, and then you add 1 to make up for this thing that's not covered. All right. Now this integral, it's also super important. You've surely seen it if you've taken a calculus course. It has a nice form. It's the natural logarithm of n. So h of n is less than or equal to, the integral is the natural logarithm of n, and we have 1 plus that. So h of n is less than or equal to 1 plus the natural logarithm of n. And actually, you can do a similar thing and just take this curve and move it to the left 1 unit. And now it looks like this. So now instead of all of the rectangles being under the curve, actually the curve is under all of the rectangles. Which means that you have this other bound, the area under the green curve, which is exactly the same as the area under the red curve. Sorry, it should stop Yeah, it should have stopped there. The area under the green curve, which is exactly the same as the area under the red curve, is this integral 1 over x dx, which is the natural logarithm of n, but that's less than or equal to the nth harmonic number. So hn is less than or equal to the natural logarithm of n plus 1, then it's bigger than or equal to natural logarithm of n. So the expected number of times that this thing executes is very close to not n, not 1, not n over 2, but actually the natural logarithm of n. So our intuition was way off. It's not halfway between these two things. For large n, the natural logarithm of n is much smaller than n over 2 or even n minus 1 over 2. But we know it almost exactly. It's sandwiched between these two numbers here. So very small. And there's a lot of algorithms and data structures in computer science that make use of exactly this fact. In fact, if you are taking the data structures course with me right now, you've seen random binary search trees and their related thing, treeps. Natural logarithm of n showed up when analyzing those things, and it's exactly because of this. So it's for exactly the same reason. So important thing to look up for. Why can't we extend the red curve upward till it touches the y-axis and then find the integral from 0 to n? We don't want to do that because if we extend it upwards, it goes up to infinity. So this chunk up here and everything under it is much bigger than 1. So we're better off, rather than extending it, stopping here and then just adding the 1. We know what this is. It's just 1. We want the best bound that we can get, so stop here, count all of this, so that's the half plus a third plus a quarter and so on, and then don't forget to add an extra 1 for the one that you didn't count. Okay, so that's it for today. Any further questions? Okay, so thanks everybody for showing up today. It's always nice to have some kind of audience when we're teaching.